Hello everyone, we're going to talk about section 7.3, which is Introduction to Probability. So in probability, an experiment is an activity or occurrence with an observable result. So each repetition of an experiment is called your trial, and the possible results of each trial is called an outcome. Now the set of all possible outcomes for an experiment is the sample space for that outcome. So essentially, for your sample space, it's going to be every possible outcome that you can get during your experiment. But once again, no duplicates unless specified. So your sample space will just be all the range of the different results you could have gotten from your experiments. So like for example, if you toss a single coin, the only outcomes you can get are heads or tails. So we can call heads H and tails T. You can leave them as heads and tails, but a lot of times you'll see that they're simplified down to either much shorter words or just maybe a letter. So we have heads as H and T as tails. So in this case, our sample space, which we normally will call S, will be S is equal to the set of H and T, because those are the only outcomes. So those are going to be the only things in the sample space. All right, so let's do one example just working with this idea of a sample space. So for example 1, we just want to give the sample space of each experiment. So we're going to have different experiments, and we're just going to try and figure out what the sample space is going to be. So for A, we have a die is rolled. This means a single die is rolled. Well, we know that a die has 6 sides, and it's numbered from 1 through 6. Now, we can roll this die 100 times, or let's say 100 trials. We can do this a certain number of times, but we know that the only options we're ever going to get when we roll a single die is going to be a 1, 2, 3, 4, 5, or a 6. So, since we know this, we can say we know the only outcomes of rolling a die we'll be getting a 1, 2, 3, 4, 5, or 6. So our sample space, and once again we're going to call this S, is going to be S is equal to the set of 1 through 6. So we have S is equal to the set of 1, 2, 3, 4, 5, and 6. Because even if we roll this die 100 times, so we have 100 trials of an experiment, we know that these are the only outcomes we're ever going to have, because your die can't magically come up with 7 or 8 or 0 or anything along those lines. All right, so moving on to B, we have in a public opinion poll, respondents are classified as young, middle-aged, or senior, and as male or female. So in this case, we have 3 categories for essentially age, and then we have 2 categories for gender. So what we're going to see here is that since there are 2 categories we're taking into consideration, we can say these outcomes can be written as ordered pairs. And what the ordered pairs allow us to do is to match each one of the different categories with the other, because we're thinking of all the different outcomes. So we're thinking of all the different outcomes that we can have. We need to think of, okay, let's take one category, match it with each of the others, and then the other category match with each of those others. So in this case, we would need to have a young male, a middle-aged male, a senior male. So now we have all the males. So now we go on to females. So we would need to have a young female, a middle-aged female, and a senior female to create our sample space. So, I can write this now. So we say our sample space S, we set up our set for our curly brackets, and we're going to write these as ordered pairs. So we're going to have them in parentheses. So remember, let's start with male. So we can say young male. All right, let's put a comma because this is an ordered pair. Then we're going to have middle-aged male. Then we're going to have senior male. So now we've established one gender, male, with every category of age that we have. So now we do the same thing for female. So we can take a young female, a middle-aged female, and a senior female. Oh, there we go. And that concludes our set because that's every category, that's every combination we can have of the two categories. Because you know that you can't have two categories in the same thing. You can't be young and a senior or something along those lines. So we know we have now matched each category with all the different subcategories as well. So we know that these are all the outcomes we could possibly have no matter how many times we run this experiment. All right, so for C, we have an experiment consists of studying the number of cats and dogs in homes with exactly 4 animals. So what we can do here, if we know it's always going to be exactly 4 animals, and it's going to be different numbers of cats and different numbers of dogs, we have to think of all the combinations that we can have. So starting with our sample size, if we start with dogs, and we know there's exactly 4 animals meaning cats or dogs, we can start with saying, okay, well, what about 4 dogs? So we can say 4 dogs. Now we think, okay, what about 1 less dog and, one less dog and 1 more cat. So then we have 3 dogs and 1 cat. So I'm going to write 1 cat. Now we'll have 2 less dogs. So we can say 2 dogs and 2 cats. Another dog less, so 1 dog and 3 cats. And then we can finish this off by saying we have a household full of cats. So 4 cats and no dogs. So this would be an example of our sample size. So we can see we start with 4 dogs, we end with 4 cats, we find all the combinations in between. But now we want to think about that we can also include the order in which they were adopted. So we can let D equal dogs and C equal cats. Then there's only going to be one answer for a home with 4 dogs and 4 cats, but the combinations are going to change. Because we see, if we have 4 dogs and 4 cats, it's not really going to matter in the order that we adopted them, because it's just going to show up as dog, 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 or cat, 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 cat. But in the case we have 3 dogs and 1 cat, there's going to be different combinations in order of adoption. So let's say, well, maybe you adopted the cat first, and then you adopted a dog, and then another dog, and another dog. Maybe the cat was last, maybe the cat was second or third. So we have to take into consideration all these different combinations if we're thinking about the order. So we're going to leave D equal to dogs and C equal to cats so that when we write this out, we're not, taking a whole lot of room or anything. So let's say that this was our sample size 1. So now we're writing our sample size 2. So let's start again with 4 dogs. We're going to follow the same order, and we're just going to think of all the different combinations. So if we think of 4 dogs, order doesn't matter. It's going to be D, 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 D. So we have 4 Ds. Now we move on to 3 dogs and 1 cat. So we need to find all the combinations of this one section or one subset here of 3 dogs and 1 cat. So let's say that we adopt the cat last. So let's say dog, 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 cat. Okay, well that's 1. Now let's do the cat is 3rd. So we can say dog, dog, cat, dog. Now let's say the cat is 2nd. So dog, cat, dog, dog. And let's say now the cat is 1st. So you can say cat, dog, dog, dog. Now we see here in these 4, we still have 3 dogs and 1 cat, just like our second value here in our first set. So all of these still correspond to that one value. It's just now we have the different combinations. So this is what we're going to be doing for the rest of them. So now since we found those, let's move on to our next one. So we have 2 dogs and 2 cats. So let's say we adopted dogs first and cats second. So this would be dog, dog, cat, cat. And now we can just flip it. Let's say we adopted the cats first and the dogs second. So we can say cat, cat, dog, dog. And now let's alternate, starting with dog. So let's say dog, cat, cat. And let's get same thing, alternating, but flipped. So now we have cat, dog, dog. Now we know that these 4 will correspond to this value here. I'll also highlight this one here. So we know these 4 correspond to that value. Now we can go on to our next one where we have 1 dog and 3 cats. Let's continue down here. So we're going to essentially do the same thing that we've been doing. We're going to come up with all the different combinations. So let's say that that 1 dog was adopted first. Then we get dog, cat, cat, cat. Then the dog is adopted second. So we get cat, dog, cat, cat. Now we say the dog is 3rd. So cat, cat, dog, cat. And now we say that the dog is last. So we get cat, 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 dog. And let's highlight this as well. So we see that these 4 correspond to that value. All right, and now we just have our very last value, which is 4 cats. So we know since it's all 4 cats anyway, we just have one leftover value for that. And we know that's just cat, 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 cat. All right, so we see here that we have all these different combinations now of all of our different terms. All right, so now since we found our set 2, where we found all of our different combinations in correspondence to the order of adoption, we're going to assume that each of these results are equally likely. Now, in our computations, unless stated otherwise, we will always assume that each result is just going to be equally likely, even if it may not be. So a word of caution, an experiment may have more than one sample space, like in number 1C, like in the one that we just did, because we see here there's 2 sample spaces, one in which we just have all the different outcomes without order, and then our second where we have all the different outcomes with order. The most convenient sample spaces have equally likely outcomes, but it's not always possible to choose such a sample space. So, in certain cases, it will be necessary that not every single outcome is equally likely, but the best sample spaces are when the outcomes are equally likely. So unless stated otherwise, we will assume that they're all equally likely, but it's not always the case. So always pay attention for that. All right, moving on to events. So an event is a subset of the sample space. So basically, when we were thinking about sets back in section 7.1 and we discovered subsets, we know that those subsets are just sets within the set. So events are just subsets in the sample space. They're just called something different now, since we're now calling our set the sample space instead of the set. So we're calling them events instead of subsets. But events are to sample space, as subsets are to sets. So you may get a little confused about them at times, so just remember that they are the same thing as subsets. So if the sample space for tossing a coin is S is equal to the set of H and T, then one event, E in this case, is going to be the set of heads, or just the set of H. This represents the outcome of heads. So this event is saying that, okay, well, this event, you tossed heads, something along those lines. But we see it as just a subset. So like in example 1A, where 1A we had rolling the die, a sample space of a die being rolled is S is equal to 1, 2, 3, 4, 5, and 6, which we already found. We assume the die rolls fairly, and so possible events are going to be what follows. So when we say we assume the die rolls fairly, you can actually purchase dice that will roll unfairly, and that means that it will be weighted differently so that you'll constantly roll different values. So when we talk about a die, we're talking about dice that roll evenly, not dice that are weighted in any sort of ways. So we have some possible events. So these are going to be our subsets. So let's say the odds we roll an even number. So that event, which we can call E1, is going to be the set of 2, 4, and 6. Then we can say, well, what if we roll an odd number? So that would be E2, or a second event, and that would be the set of 1, 3, and 5. Then we have roll a number less than 5. So our third event, or E3, is going to be the set of 1, 2, 3, and 4. Then we have roll a number divisible by 3. It's going to be our fourth event, and this will be the set of 3 and 6. So using our definition of N of A from section 7.1, where we use this to count the number of elements in our set, we're going to see that N of E1, our event 1, which was rolling an even number, is going to be equal to N of E2, which is rolling an odd number, and those are going to equal 3, since we see that there are 3 elements in each of those sets. Then we see that N of E3 is going to equal 4, because we have 4 elements in the set. And then we see that N of E4 is equal to 2, so you see there's only 2 elements in the set. So we can use the same definition for events and sample spaces as well. All right, for example 2 here, we have 3 coins are tossed, and a head and a tail has to be recorded. So this means that every time we roll, or sorry, we're flipping coins, not rolling dice. Every time you flip 3 coins, you have to have a head and you have to have a tail. So those are kind of like our parameters in essence. So has to be recorded for each coin. Then we write the event E as the coins show exactly 1 head, and the event E2 as the coins showing 1 tail, and E3 as the coins showing either all tails or all heads. So in cases like these, the order is going to matter, because we're not tossing 3 coins at the same time. We're going to toss them one at a time. So for E1, we want the event as the coin showing exactly 1 head. So let's say E1. And we know that order matters, and we're flipping this 3 times. So if we're only considering 1 head, then we can start with that. So we can say, okay, well, maybe there's 1 head. I'm going to write this out as a capital H. You can see them written as lowercase or uppercase letters, and it doesn't really matter. But we'll say head is H, and a capital T is tail. So let's say we start with flipping the head, and then we have 2 tails, because it's 3 coins. Then let's say we have a tails, then a heads, and then a tails. So we get tails, heads, tails. And let's say that we flip our heads last. So we get tails, tails, head. And that would be our event space, because we know that if we're tossing 3 coins, our sample size is going to be much larger, because we have other ways that we can flip these coins, but we're only paying attention to when we will flip a heads just once. So now let's do event 2. And event 2, we want to show that we're flipping one tail. So it's essentially the same thing, except now we have one tail instead of one head. So for E2, we can do the same thing. Let's say that we flip that tail first. So we have T, then we'll have 2 heads after that. Then let's say we flip the tail second, so we get a heads, a tails, and a heads. And then we could say that we flip the tail last. So we get a heads, heads, tail. Now for E3, we want the coins showing either all tails or all heads. Since we know it has to be all tails or all heads, there's only 2 ways, so there's only one way to have each one. So we know that E3 is just going to be the set of all tails or all heads. So in this case, if we wanted to know the number of elements, if we took n of E1, that would be 3. If we took n of E2, that would also be 3. And if we took n of E3, it would be 2. So it's only 2 elements. All right. So we see that the combination of all 3 events and the sample size of the experiment above, an example that we just did, so the combination of all of these is our entire sample size. Then we see if an event includes the entire sample size, that is called a certain event. Since the event are sets, we can use set operations to find unions, intersections, and complements of events. So going back to a certain event would be if your event size was the exact same thing as your sample size. That would mean that a certain event would be, we are absolutely certain that this event is going to happen because these are the only likely outcomes. So when we think about that, that's what we're talking about when we think of a certain event. We know for certain it will happen. So now here's a summary of all the set operations that we've learned from our previous sections. So we have let E and F be events for a sample space of S. Then we have E intersects with F occurs when both E and F occur. Then we have E union F occurs when E or F both occur. And then we have that E complement occurs when E does not occur. So for example 3 here, this is also going to be example 4 and a combination of your turn number 3. We have minimum wage workers. So a study of workers earning the minimum wage grouped such workers into various categories, which can be interpreted as events when a worker is selected at random. Consider the following events. E, a worker is under 20. F, a worker is white. G, the worker is female. And then we want to describe the following events in words. So the events that we're going to go through now, these will all just be described in words instead of numbers or letters. So for part A, we have E complement. Now, if we want to find E complement, we know that E complement is going to occur when E does not occur. We know that E is thinking about when a worker is under 20. So if we're thinking about our complement, it means that our worker cannot be under 20. So E complement, we know that this is the event a worker is 20 or over. Because also, if we kind of try and imagine a Venn diagram, we can think that E would be the set from 0 to 19. And so everything that's not 0 to 19 is going to be our complement. So we know it's going to be 20 or more. Then we have B, which is F intersects with G prime. So it's important to start by thinking, what is G prime? So G is when a worker is female. So G prime is going to be when a worker is not female, or typically that worker will be male. So we have F intersect with workers that are male. We know that F is workers that are white, we know that intersect means that they have to be both. So we get that a worker is white and the worker is male. So when you write this, we can say that this is the event that a worker is white and not female. So the worker is a white male. All right. So now we have C. So we have E union with G now. And our union is when F occurs when E or F or both. So we know E is the workers under 20. G is the workers that are female. So this means that the event a worker is under 20 or a worker is female or a worker is a female under 20. So we have all of them. So we know that the event is a worker under 20, so any worker under 20. Then we have a worker that is female, so any age that's female, or a worker that is female under the age of 20. Now for D, we have E prime intersects with F prime. So we know that E prime, which we figured out in part A, is an event that a worker is 20 or over. We know that F is when, or the event that the worker is white. So F prime is going to be the event that the worker is not white. So we have for part D, we have the event, and remember it's intersection, so it's going to be both. So we have the event that a worker is 20 or over and not white. So you have the event. A worker is 20 or over and non-white. All right. So that's how kind of we describe each one of these events with words. So now we say that two events cannot occur at the same time, like rolling an even and an odd number with a single die roll. And these are called mutually exclusive events. So we see that mutually exclusive events, we have events E and F, are mutually exclusive if E intersect F is equal to the empty set. And this is because if they cannot occur at the same time, that means that they will not have, they will not have any of the same elements. And if they don't have any of the same elements, then the intersection would be the empty set. So an event E and its complement E prime are mutually exclusive, since we have that you can't have the event and its complement happening at the same time, because you have events that are in E and then you have events that are in E complement. So they can't occur at the same time. So another example is when you're rolling a die, you know that your set is going to be 1 through 6, or your sample size, and let's let E equal the set of 2, 4, and 6, so the even numbers. Then we let F equal the set of 1, 3, and 5, or the odd numbers. So we say that E and F are mutually exclusive events, so that E intersection with F is equal to the empty set. This is because when you roll one die, you're going to get an odd number or you're going to get an even number. You can't roll an odd and even number. So we know that these things are mutually exclusive. All right, so moving on into probability. So for sample spaces with equally likely outcomes, the probability of an event is defined below as the basic probability principle, we have let S be a sample size of equally likely outcomes, and then we're going to let event E be the subset of S. Then the probability that event E occurs is P of E. This is how we're going to signify the probability. We're going to have a capital P outside, and then we'll have parentheses, and whatever we're taking the probability of be inside the parentheses. So we have P of E is equal to N of E divided by N of S. So we know that N of E is taking into consideration the number of elements inside the set of E, and then we have the number of elements inside the set of S. So, a word of caution, the basic probability principle only applies when the outcomes are equally likely. So if you ever get a question that says or specifies that the outcomes are not equally likely, then we can't use the basic probability principle. All right, so on to example 4. This is also going to be numbers 35 through 40 in your book. So we have a jar contains 3 white, 4 orange, 5 yellow, and 8 black marbles. If a marble is drawn at random, find the probability that it is the following. So we have A through F here, so we have white, orange, yellow, black, not black, orange, or yellow. So what we're going to do is we're going to let W equal white, O equal orange, Y equals yellow, B equals black, and S is going to be our sample size. Then we say that N of S, or the number of elements in S, is going to be the combination of each outcome. So we know that we would take N of W, or the elements of W, N of O, N of Y, and N of B, and we're going to add them all together because these are only outcomes. So if they're all subsets, we're going to add all of the subsets together, all the elements of our subsets, and we get that our N of S is going to be equal to 20. So our sample size is 20. All right, starting with our first value here. So if we want to take, because we want to find N of W, and we know that our jar is containing 3 white marbles, then we know that our N of W is going to equal 3. There's only 3 marbles in our whole jar. So using our basic probability principle, which we know is going to be P of our event, which is P of W, is equal to N of W divided by N of S. We know N of W is 3, we know N of S is 20, so we get that our probability is going to be 3 over 20. Now we can calculate this value in percentages if we would like, but we don't have to, so we're just going to leave it as 3 over 20. So now moving on to orange, we want to take N of O, which we know from our question, we know there's 4 orange marbles in our jar. So we know that N of O is going to equal 4. And then we'll just use our probability principle. So P of O, or the probability of drawing an orange marble out of the jar, is equal to N of O divided by N of S. And we know N of O is 4, N of S is 20, so we have 4 over 20. Now we can simplify this just a little farther. We say that this is equal to 1 over 5. So you normally want to simplify down to its most simplest form when doing these problems. So for part C here, we have yellow, so we know N of Y, since we know there's 5 yellow marbles, we know that's going to be equal to 5. And we have our probability of drawing a yellow marble is the number of yellow marbles divided by our sample size. So it's going to be 5 divided by 20, which in this case is going to be 1 over 4. Then for our last colored marble, we have 8 black marbles. So we have N of B is going to be equal to 8, since we know there's 8 black marbles in the jar. And the probability of drawing a black marble is going to be equal to the number of black marbles divided by our sample size, which is going to be 8 divided by 20, which is also 2 divided by 5. All right, so now we have the probability of drawing singularly each marble. Now we have our other two, which are kind of combinations. So for part E here, we have not black. So we are trying to find the probability of drawing any marble that's not black. So if we have 8 black marbles, and we know that our jar contains 20, what we're going to do is say n of, we'll say not B is going to be our sample size minus our number of our black marbles. So we're going to have 20 minus 8. And that's going to be equal to 12. So now we get to do the same thing. We'll say the probability of drawing a marble that's not black is equal to our number of non-black marbles divided by our sample size, and that's going to end up being 12 divided by 20. Or when we simplify this down, same thing as saying 3 divided by 5. All right, so lastly, we have orange or yellow. So if we're thinking in this case, orange but not, or yeah, sorry, orange or yellow, we're thinking of our union because we want orange or yellow. But if we're thinking about our union, we know our union is one thing or another or both. Well, if we draw a marble, it can't be orange and yellow. So this is what we were talking about when we think of mutually exclusive. So one can happen or the other, but they can't happen at the same time. But it's still our union. So what we're going to do is say that this is going to be N of O union Y. Then, if we just want it to be orange or yellow, we know that there are 4 orange marbles and 5 yellow marbles. Okay. 4 plus 5. So we know that this is going to equal 9. And this is going to give us the probability of orange union yellow is equal to the number of orange or yellow marbles divided by the sample size. And we're going to get 9 over 20. Which I think that is it. Yeah, that is the most simplified time too. 9 divided by 20. All right, so since we kind of made a note about this, let's say something. So we say that these events are mutually exclusive or disjoint events. So they're disjoint because they don't share any of the same elements and they can't happen at the same time. So they're disjoint, or the definition that we just learned, which was mutually exclusive. We'll keep going with that actually. And we know this since they don't contain the same elements and They can't occur at the same time. So, since we know that they're disjoint or mutually exclusive, we can use our union rule, which we learned from our last section, which stated that if we just want to find the elements, if we just wanted to find elements and they're disjoint, this is the same thing as saying n of O plus n of Y. And that's what we did in this case. We did it without really talking about it, but that is what happened. So because we got to do this, and we're thinking of the orange or the yellow marbles, and we got to use our union rule, we know that we end up with 9 divided by 20. But also, we just use kind of our reasoning that we've learned just from all of our previous sections, and just with common knowledge that if we wanted to draw an orange or yellow marble out of a draw of 20, we know that we have however many marbles there were of orange plus how many there were of yellow, and if we're just drawing one at a time, we're thinking of either one of these, so we just add the values together. So we were able to do this by just reasoning it out, but there is a reason behind this. We could have used the union rule since they were mutually exclusive events. Also, it was not mentioned, but for part E, when we were thinking of our marbles that were not black, that's also like saying B complements. This is the same thing as if we were finding the elements of B complement. All right, so moving on to another example here, we have just a little blurb here about standard decks of cards. Example 5 is also going to be numbers 26, 32, and 34 in your book. So our blurb here just states that a standard deck of 52 cards has 4 suits: hearts, clubs, diamonds, and spades, with 13 cards in each suit. The hearts and the diamonds are red, the spades and the clubs are black. Each suit has an ace, a king, a queen, a jack, and cards numbered from 2 to 10. The jack, queen, king, and jack, queen, and king are called base cards, and for many purposes can be thought of as having values of 11, 12, and 13, respectively. The ace can be thought of as the low card of value of 1, or the high card, value 14. See figure 17, which was not included, and then we're going to refer to the standard deck of cards in our discussion of probability. So, a card is drawn from a well-shuffled deck of 52 cards, and we want to find the probability of drawing the following. In the case that we're working with our questions here, we are going to assume ace is low or has a value of 1, just in our case here. So, a card is drawn from a well-shuffled deck of 52 cards, and we want to find the probability of drawing the following. So we want to find the probability of drawing a black card. So if we want to find this probability, we know that we can label this as the probability. It's P, and then we can write anything in our parentheses. So in this case, I'm just going to straight out write black card. So if we have this, and we know that there are 4 suits in a deck of cards, 2 of which are red, hearts and diamonds, 2 of which are black, clubs and spades. So if we have these 2 suits, we know that each suit contains 13 cards. All we have to do is multiply 13 by 2. So the probability that we get a black card is going to be n, the number of all black cards, divided by our sample size, which is going to be 52. So our number of black cards, we know there are 2 suits, each with 13 cards. Our sample size is 52. And what we get here is 26 divided by 52, which is just 1/2. This makes sense since each suit has the same number of cards and there are 4 suits in a deck. So if we wanted a single black card, we know there's a 50% chance of pulling a single black card since that was half the deck anyway. All right, now moving on to part B, we have a black 7 or a red 8. So we're going to write this out. Say probability of black 7 or red 8. So we can decipher some things here first. So we know there are 2 black 7s and 2 red 8s. This is because we know that there's 2 suits of black cards and 2 suits of red cards, so that means that there's going to be one black 7 in each of the suits and one red 8 in each of the suits. So since we know these values, and since we know that there's 2 black 7s and 2 red 8s, when we find our probability, this is like saying the number of black 7s plus the number of red 8s divided by our sample size. Now, by saying the number of black 7s plus the number of red 8s, this is the same thing as saying the number of elements in the probability of a black 7 or a red 8. And since we know there's going to be 2 of each, this is same thing as saying 2 plus 2 over 52 is going to equal to 4 over 52, which is equal to 1 over 13. So we have a 1 in 13 chance. All right, then our last value here, we're guessing a spade or a king. So we have the probability that we will draw a spade or a king. So this is pretty much going to be something similar, but we know there are 13 cards in the spade suit and 4 kings in all. But the thing that we notice is that if we're considering our 13 cards in the spade suit, one of those is going to be the king, or the king of spades. So if we had our entire range of elements, remember we don't count duplicates. So we wouldn't count the king of spades twice. We'd only count it once. We only want to count our king of spades once. So this essentially is going to be the number, or the number of elements of getting a spade or a king is equal to, let's consider all of our spade cards first, and 1 less king. And that's going to give us 16. So when we write our probability of a spade or a king, we take the number of elements that we would get if we got a spade or king. And we're dividing this by our sample size. We know that the chances of getting a spade or a king would be 16 divided by our sample size of 52, and this is going to simplify to 4 divided by 13. So when we're thinking logically about these applications, we have to think about the duplicates that there might come about. So moving on, we see that in the previous examples, the probability of each event is going to be a number between 0 and 1. These were all fractions, but if we calculated each of these fractions, we would find that the probability would be between 0 and 1. This represents having a 0% probability and a 100% probability. You can't have a negative probability, and you can't have a probability more than 100, so that means that every time we calculate our probability, it has to be between 0 and 1. So this is true in general for any event. We say any event E, the probability of E is going to be between 0 and 1, including 0 and 1. So you can have a probability of 0, and you can also have a probability of 1. You just can't go above or below. So we think about this, a certain event has a probability equal to 1, and a certain event is when we have an event that its entire set of elements is the same as the sample size. So we know that anytime we get any one of these things in our event, it's going to happen because they're all in our sample size. Then we see that an impossible event has a probability of equal to 0. This would be the probability of someone reaching 10 feet tall. That would be a probability of 0. Then we can go on into our empirical probability. So in many real-life problems, it's not possible to establish exact probabilities for events. So we're going to make useful approximations by drawing on past experiences, and these are called empirical probabilities. So as we know, life in itself is just messy. Not everything is going to be in perfect numbers and values all the time. So a lot of times we use empirical probability to think, okay, well, what was the percentage in the past? And we're going to assume that this will be the percentage in the future, the probability in the future. So for example 6 here, which is also number 57 in your book, we have causes of death. There were 2,468,435 US deaths in 2010. They are listed according to the cause in the following table. If a randomly selected person dies in 2010, use this information to find the following probabilities. So for the causes we have heart disease, cancer, chronic lower respiratory disease, cerebrovascular disease, accidents, Alzheimer's disease, diabetes, mellitus, influenza, and pneumonia, and then we have all other causes. So we have all these different causes of death, and then we have our overall numbers. So for part A, what we want to do is find the probability that the cause of death is heart disease. So we're going to let H equal heart disease. And what we're doing is we're finding the probability of H. Now, we know our sample size. Our sample size is 2,468,435. So we're going to let H equal heart disease. N of S will be 2,468,435. And then we're going to let N of H be the number of deaths from our chart. So we have 597,689. So if we want to find the probability of dying from heart disease, what we're going to do is find our basic probability. So we know that this will be N of H divided by N of S. And we have that N of H is equal to 597,689. We know our sample size is 2,468,435. That's very long. And now we want to use a calculator, normally used to calculate these. And these are going to be in percentages because it would take quite a long time to try and find an even fraction. So if we calculate this in order of decimals, we end up getting that this is 0.2421. Or this is the same thing as saying 24.21%. All right. Then for part B, we have the probability of the case of death was cancer or heart disease. So we want to let C equal cancer, and then we'll let N of C equal 574,743. So if we want to find the probability that it was cancer or heart disease, we know that taking the union will take into consideration one or the other. But we know that union also considers both. For the sake of our problem, we're going to assume that these are mutually exclusive events. We're going to assume that if someone dies of heart disease, it's not also because of cancer. So, we say assume mutually exclusive events. So if we assume mutually exclusive events, and this is like saying the probability of C union H. So we can use our union rule to get N of C union of H is equal to N of C plus N of H, since they're disjoint. So we're just adding these values together. So we see that N of C plus N of H is going to be 574,743 plus 597,689. When we add these values together, we're going to get 1,172,432. So when we find our probability of cancer union heart disease, or C union H, we know that, I'm going to bring this down. We know that this is equal to N C union H over N divided by our sample size, so same thing as saying N of C plus N of H divided by our sample size is 1,170,432 divided by 2,468,435. Now I want to use a calculator to calculate this value, and we end up getting 0.4750, or if you wanted it in percentages, 47.5%. All right, so last question, part C, which let's bring down here. We have the probability that the cause of death was not an accident and not diabetes mellitus. So if we're thinking about not diabetes and not an accident, we know that if we let A equal accidents and D equal diabetes, we want A complement and D complement. We can think of this as actually a few different ways, not necessarily just the complements. Since we want A complement and D complement, we know that that would be A complement intersected with D complement. Now, using an intersection in this case would be more difficult. So what we're going to do is essentially just subtract our values of A and our values of D from our sample space. Since we know that those are the certain numbers of those deaths, we're just going to take them out of the equation. So we're going to take N of S and subtract N of A plus N of D. And this is going to be an easier way that we can do this. And this is also a way that we can just think logically, because if we're thinking of really anything other than having diabetes or it being an accident, then what we're considering is everything else. So if we want to find N of S minus N of A plus N of D, what we're going to do is take 2,468,435, and we're going to subtract the sum of these two values. So we know that accidents account for 120,859 plus diabetes, which accounts for 69,071. So we want to find these values. So if we simplify this a little bit, we're going to get our sample size here minus 189,930. And this is going to give us 2,278,505. So what we want is our probability that it's not A or D, D, capital D. So this is going to be equal to the number of elements that are not A or D divided by our sample size. And we know that the number of deaths that are not accidents or diabetes is 2,278,505 divided by our sample size here. And when we calculate this value in decimals, we get 0.9231, which if you want to put in percentage, is 92.31%. All right, so we learned a little bit about the basics and beginnings of probability, and we put these into practice. So that pretty much concludes our section 7.3 here. So as always, if you have any questions about anything, feel free to email me or pop into my office hours or send in an anonymous question form or anything along those lines. So I will see you all virtually later.